Good morning, everyone. Today I'll be speaking about CNN-based boundary detector for remote sensing images. I'll take you through the process of developing the boundary detector. I think it will be most useful to everyone to understand the process on how to get to a solution when you face a problem, especially on lessons learned when we developed such a detector for remote sensing images. So the outline of the presentation today will start by the introduction, proposed methodology, some experiments, and conclusion. First of all, let's define boundary detection. The aim of a boundary detector is to find a contour that separates one object from another. Generally speaking, there are two approaches to boundary detection. One approach is that you try to find changes in pixel value and try to find the contour itself, or where is an edge or a change. Then you try to separate the image for further processing, etc., where you deal with objects themselves. So boundary detection is, I would assume, is different than edge detection. Boundary is the boundary of the object. Edge is anything that constitutes an edge. The other approach, so one approach is to find the changes, the variation in the pixel value. So you try to find an edge, and then you group these edges, etc., to find contours or object separation. The other approach is to find objects, try to group homogeneous regions within the pixel values, and you assume that where they interconnect, here you have your boundary. So these are two approaches of approaching the problem. The first approach, where you find edges, the problem you face normally is when you have textured environment. Especially, you have lots of textured environment, like, for example, urban areas could have buildings, etc., roads, cars, different objects that could have edges. Maybe you are interested only on the urban environment, so these edges in between you are not interested in. So the separation could be a problem for you when you deal with the only edges. The other approach, when you deal with regions or try to find objects first, and then you find where they interconnect or connect with each other, is that you might not get the actual accurate boundary. Maybe it will be displaced. So these are two approaches to the problem. And our work here is we are trying to kind of combine both, as we will see in the presentation. In terms of applications of boundary detection, you can do change detection. For example, if you have shoreline and you want to monitor it, then you can monitor it across time using the boundary detector. You try to detect the shoreline, and if you detect it in another image after a while, and then you see the difference. If there is a difference, there is a change, etc. It encapsulates more than just change detection. It could be also monitoring, as in the given example, or you try to monitor the urbanization. It's another example where you try to find where the forests are, deforestation you have, the urban area, whether it's increasing or not. Then you try to find the boundary of that area, and then you compare it across images to see and monitor the progress. You could also do target detection. For example, like you have a sea, you try to detect ships. If you find boundaries within the sea, then there must be something of interest over there. So we could use it also for target detection. These are some of the applications of boundary detection. And in principle, boundary detection might be the first step in many further image processing, let's say, image processing steps when you analyze a remote sensing image. The current approach when you design a boundary detector is that you try to incorporate multiple features. For example, as here mentioned, the shape, color, and texture. So you try, if you are trying to find, for example, the urban area or the shoreline, then you try to find, for example, you encode for the shoreline maybe a certain characteristics of the color, a certain texture of the sea, etc. So you try to encode as many as you can to get a good boundary detector in that case. It depends on your application. So the challenges that we have when we have, for example, new imagery, or we have new application, or we have new requirements, or a new feature descriptor gets created or developed, then we would need new methods. So each time we have variation in one or many of these parameters, let's say, or inputs to our problem, we usually go through the development of boundary detector once more. The challenges, as I've said, sometimes the sensor, it's sensor related. So we have different sensor characteristics. Maybe the pan sharpened band in one sensor is different characteristics, different resolution, different, etc., than another sensor. Another variation could be application related. Am I designing a boundary detector for a particular purpose, or it is more of a generic? So if you define it for a specific purpose, then you lose. It's no longer generic. You cannot use it for other purpose, or it might be of less optimal. When you design it as general, then you try to fit it to many applications, but it might not be also optimal in this case as well. The other one is data related. So when you deal with different spatial, radiometric, and spectral characteristics of the sensors, you face new challenges. So you design for example, the pan-sharpened image, or the multispectral, then you get another, or will it remain the same for different bands? So if I develop a boundary detector for the pan-sharpened image, will it work as good for the different bands in my multispectral image? If it is from radar image, will it work on the same way? Or it will have degrading performance as we change the data itself, even within the same sensor. The other one is the content related. So if you have two regions that there are smooth transition between these regions, would I be capable of recognizing such regions? Should I look into the micro details, or I move up and see it from more of like bird's eye view of the image? So it creates a problem for me to detect a boundary detector and remain accurate, specifying the correct boundary. Here it comes the convolution neural network. I think you are familiar with convolution neural network, but just for a matter of introduction, it is one of the deep learning techniques introduced in the machine learning community. The beauty of it, it's an end-to-end machine learning technique. Previously, when you would design a machine learning technique, you would have feature descriptors. Feature descriptors are manually engineered. So you have a set of features that you would expect to give you a good boundary. It would detect a boundary or an object. Then you feed it into a network to see which one, or to combine these features together to get you to the final answer, to the final classification. For the convolutional neural network, this process is done automatically. So you feed it the input and you supervise the output. You tell it, okay, this is the output I want, this is the input I have. There is no engineered feature descriptors in the middle. So this is the beauty of it. So you can feed it an input and you expect a certain output. You try to learn it. The features actually get also learned within the network. So the idea is, what if we could use the CNN, the convolutional neural network, to try to learn the boundaries between objects, regions? This would allow us to have a feature-independent and parameter-free boundary detection. So we don't need to put any features there. We don't need to set any, let's say, parameters in that network. And the parameters will be learned automatically by the network itself. The convolutional neural network, as I've said, it operates on low axes without the need of explicit feature detection process. So there is no human experience, let's say, in engineering these features required. And then we use CNN to classify images, the pixels themselves, into boundary and non-boundary pixels. We would like, what we hypothesize here is that this will lead to a good boundary detector. Let's go through in deep little bit on the block diagram of the proposed methodology. So if we start here, we have the input image. We have the multispectral bands. So we have different bands, it depends on our images. We have also here a group of convolutional neural network, a committee, let's say. So each band will be fit into many convolutional neural network. The same thing is repeated till we reach band Z, which is the last band. For each network, we will get a confidence map, which will show us the edges. We would combine all edges into one image, and we call it a fused confidence map. We set a threshold, and we get our boundary map. We'll go into this methodology one by one, and you see, to describe it in a little bit further detail. So the first step is that we have the input image. And in remote sensing, we have multispectral images. So we have different bands. What we will do is, as we've explained just a little while ago, that we'll take each band alone. So we'll take one input out of it. We will expand it to get the corners. And then we will have the patch, which is 15 by 15 pixels patch. That would run, the input is not the full image for the convolutional neural network. It is rather a small patch of 15 by 15 pixels. So the patch will move around the image until it reaches the end. And we repeat the same for each band. We will have two types of patches. One we call the boundary patch, and the other one we call it the non-boundary patch. The boundary patch where the center pixel is the boundary pixel. So in the first batch, you see if we mark the center here, it is a boundary pixel. And for the other batch, the center pixel is non-boundary pixel. We have a training set for that. So we would recognize where the boundary and how many boundary batches we have and how many non-boundary batches we have. The problem is in almost all images, you will get so many non-boundary batches, but little boundary batches in comparison. So here, this is from an actual image of 15 by 15 pixels. And as you can see here, it's called a boundary batch because the center pixel is a boundary pixel, and here it's non-boundary from the actual image. The problem is that we don't have a balanced kind of training set. We have so many non-boundary batches, but very little boundary batches. So we have to increase the number of boundary batches. What we will do is that we'll create variants. We'll take each batch and try to rotate it, flip it, mirror it around the horizontal axis and around the vertical axis. So we have different variations, and we reach around 150,000 batches in total for our data set, which is reasonable in terms of comparable networks as we have it here. So comparable networks in the literature gets trained by like approximately the same number of batches. Then we would feed it the input batch into the network, which is 15 by 15, as I've said. And then we'll do the convolutional network of 3 by 3, where we have 8 in the first layer, then convolution 5 by 5, and then we have also 8 in the second layer, then fully connected layer with 6 nodes, and then fully connected to the 2 nodes. These 2 nodes will give you, one of them will fire, one of them is non-boundary, the other one is a boundary pixel. So we'll give it the 150,000 training set, we'll feed it into the network, and we'll give it the correct answer, whether it's boundary or non-boundary. And hopefully the network could remember, let's say, or learn the assignment of how to distinguish a boundary image from non-boundary. Or sorry, non-boundary patch from non-boundary. This is only one step. As you can see from the block diagram here, I've shown you only one band, one network, and one confidence map. How would it look like? It will appear something like that, where the white pixel gives you the boundary pixel after we finish from the convolution and neural network. So you can see that you have little white dots here and there because of the texture we have in remote sensing images. But the most prominent and strong edges are around the regions themselves. So the network kind of learned the texture and ignored the texture and more focused on the edge between regions instead of getting the boundaries within each region. And in good performance. So this is one output only. So for each band, we'll have multiple confidence map, and you multiply the number of bands by the number of convolution neural network per each band, then you have multiple confidence maps. Then you try to group them. So you'll have multiple of them. Then the idea is that we need to group them all into one, because we need at the end one boundary map. There are many design choices. One of them, how many convolutional neural network per band. We tried from 1 to 6, and we will share the results in a minute. The other one is how to combine. So we have multiple convolutional neural network. How can I combine all of these into one? There are many options. We've tested 3: mean, median, and majority voting. The other design choice is should I consider all of the confidence maps, or should I select from them? What is the best option? Shall I group them all and average them all, or not? Also, the hyperparameters of the convolutional neural network themselves. Why we selected 5 by 5? Why we selected 8 in the first level and 8 in the second level? These are usually for the hyperparameter selection. These are usually set with trial and error. So you try different options, different parameters, and you see the best performance. There are many options to do that. Some of them, they are doing it in a systematic fashion. Some of them, they do random parameter initialization, etc. What we try to do is to learn from the best of the literature and try to modify each parameter separately. So we take something already working in the literature as a boundary detector and try to increase the number, for example, of levels. We put it like, I don't know, you put it, the first level is 8 or 10 or whatever. So you try to change the number and you see the effect of performance, and then you change it again, etc., until you get your network architecture fixed. So you change each parameter and so on, and then you try to find the best architecture for your problem. But hopefully, once you do it for a boundary detector for remote sensing, hopefully it would work for other sensors. It would be able to learn using the same network architecture the new parameters of new sensors. So this is the fused confidence map after we average them together, or median, or majority voting. We'll see the different options and their effective performance. From that, you can set, from this final fused confidence map, you can set a threshold, for example, etc. It depends on your application. So some of them would like to get the absolute difference between regions, then you can set the threshold accordingly. Or you are more interested into the textures and fine details of the things in your image, then you set the threshold accordingly. So it will give you one parameter to play with to set your depth of analysis, let's say, or number of edges. In our experiment, we've used the data set already published online. It would allow us to compare our work with other people's work. And we didn't set the edges. They've set the edges for us in their training and testing set. It is called the Bragg texture set. It includes different texture data sets. One of them is from remote sensing images. The images they are used from the advanced land imager, and it is a synthetic data set. So they combine automatically different regions together, as you will see in the next slides how it would look like. The resolution is 512 by 512 pixels. Each images of 10 bands. We have 40 images. We've used 30 for training and 10 for testing. So you could submit your results online. It will automatically get you the ranking across other people's work, as well as calculate for you some of the metrics of the comparison metrics. For us, for the boundary detector, one of the methods to evaluate boundary detectors is using precision, recall, and F measure. Precision is number of true positives divided by true positives plus false positives. Recall is true positives divided by the summation of true positives plus false negative, and the F measure is a combination of precision and recall. It is the multiplication of precision and recall by 2 divided by the summation. In terms of F measure, one is the best in terms of performance. So let's see how different methods. This is just to remind you of true positives. True positive is the true class is positive, and we predicted it as positive, so it's true positive. It's a boundary, and it's actually a boundary. The false positive, for example, is where the true class is not the boundary, but we recognize it as a boundary, and this is the false positive, etc. False negative, the true class is positive, while the predicted is negative, and here negative, which is the true negative. The CANI, and one of them, the other one, PB, is more recent one. As you can see, what we did is that we set the threshold to different values until we maximize the F measure for all the edge detectors or boundary detectors. So we vary the threshold value from 0 to 1, and we try to maximize the F measure. We see where is the maximum F measure we can get. And we did the same for all to allow fair comparison with all. So in terms of the F measure for CANI and PB, as you can see, it's below 0.6 in its best performance. I think it is for image 1, maybe. Yeah. For image 1, it reached around 0.6. While there are different, let's say, varying performance across other images. So we tested on the 10 images, and these are the results. But for our proposed methodology, as you can see, it's more of a bell curve. So we would believe that changing the parameter, the methodology actually gets the edges in this organized matter, or in more. So you are moving to more details into less details, etc. So it is of bell curve performance, which is nice to have across all images. And if you can see that almost all of them, if not, yeah, all of them are above 0.6, which are better performance than the other methodologies available that we compared with. This is in terms of the comparison with other edge detectors or boundary detectors. Let's look how it would look like on the image. So this is the input image. As you can see, it's a synthetic data set. So the actual difference between regions is not a natural one. It is fabricated one or synthetic. While the image itself is the image, the region here is it's taken from a remote sensing image. It's not synthetic, but this what's synthetic is the edges, these sharp edges around regions. So they take certain images or portions of images, and then they try to combine them into different edges, like this one and that one, and different shape of edges between these regions, and different sizes as well. So they also provide for you the ground truth. So we are not interested on what is inside. We are interested only to separate them in this kind of ground truth. So you separate region 1, 2, 3 in this particular set of edges. So we have what is boundary and what is non-boundary. The idea here with the texture data set is that we are trying to avoid edges within the texture and try to focus on the difference between regions. The proposed method, as you can see from this column, can find the sharp edges between regions. I flip the color so you can see that the black is the more stronger edge in comparison to the other regions or textures. When we compare to others, it seems fair to say that this is of a better performance. This is more clear and harsh and kind of separates the different regions. Here, the colors are all. It is the PB managed to get these edges and to avoid the texture, but with the varying performance, you see here this edge was not detected, which was a very difficult one. And same thing maybe here, it's very fine light when separating these regions together. Let's look at the numbers actually when we compare the different methods. So the comparative analysis here in terms of image from 1 to 10, and overall the mean F measure for the proposed method is higher than those of PB and CAN. Although there are some, like here, precision in CAN is more, but the F measure is lower, while it's higher in the proposed method. So there could be some more precision, but the F measure, which combines all, it's not that high, which confirms that the proposed method is better than the other presented here. And here we'll discuss the method evaluation. So how we came up with the number of layers. What we did, we selected 3. Why we selected 3 CNS per band? If you look at the single band, it's 0.640, while 3 CNS of higher, let's say, F measure. As you increase the number of bands or CNNs per band, then you get a higher number, a better number. Well, what we tested until 6, so 6 is the highest, as you can see, 0.649. However, if you look at the details, sometimes even 6 is not better than a single one. Here, the single one in that particular example is image 7. So what it tells us that if we increase the number of layers, we might get better performance, but this is not 100% correct across all. because we have like some examples where we have it, where a single CNN is more. If you look at the accuracy, actually it's not of that big difference. 640, 643, and 649. But why we selected 3 is that it will allow us like a compromise. If we move only to 1, we will be very susceptible to any randomization in the parameters, etc. But if we move to 6, we gain a little bit in terms of performance, but we increase the computational complexity. We'd require more resources and more time. A good compromise is where we have this in the middle. We have 3 CNNs. That's why we selected 3 in our model. So each band will run into 3 CNNs. So if we have like the data sets we have here, the Bragg texture data set, we have 10 images. 10 images, and in each image we have 10 bands. So for each image, 10 bands, 3 networks, so we have 30 confidence maps, and then we combine them into one. So we are running 30 CNNs per image to get. Let's look at other variation. What if we select mean, median, or majority voting in terms of combining image? So as I've said, we have now 3 multiplied by 10 bands, which is 30 per images. How we combine these 30 into a single confidence map? We tried mean, median, and majority voting. If we look at the numbers, we see, okay, in terms of the F measure, mean is not as good as median, while the majority voting is the worst. So in comparison between this one and this one, the performance is slightly better in median, but because of the linearity of the mean, we've selected the mean. Although it might not be the best performance, but it's of a linear performance. That's why we selected the mean as a way to combine different confidence map into one, the interfusion process. Here is an interesting test we did, is that we compare the mean with selective mean. What do we mean? The mean, we take the average of all, but the selective mean, we select from the bands, and only those with high eigenvalues could be selected. So those who are in terms of eigenvalues of a higher importance, value, we would combine them. We will not combine all, because you might get degradation of performance when you combine a bad band or output to the rest of the outputs. You know what I mean? So we discovered that selective mean, actually, this is true. Maybe across all images, if you don't combine all of them, you only combine a subset of them, you get a better performance. So that's why we selected the selective mean, and we do it using that eigenvalue to decide. These in terms of method variations. So in conclusion, we've seen a way to train a convolutional neural network to recognize edges and try to ignore the edges within textures. We managed to train the network to respect the spectral bands. So each network will be trained on a separate band in the image. Try to learn the features within that band and adapt automatically to the characteristics of that band and the characteristics as well on how our region would appear across different bands. We've also shown the improved performance of our state-of-the-art techniques. And here, the future direction, if you will, as you say, as you've seen here, that selective mean is better than mean. So how we would build something that's context aware of the band on how to select the best selected from the outputs we have, how to select the best confidence map that will lead to the best separation between regions. Can we include something about the context so we can select the bands and ignore even the non-useful bands, let's say, for our particular problem or challenge? So I'll go over the presentation quickly just to recap. So what we are trying to do is we find a contour that separate one object from the other, being the object region, etc. There are multiple applications for change detection. For boundary detection, which are change detection, monitoring, urbanization, deforestation, target detection, etc. You name it. The problem when you design a boundary detector and you take care of the shape, color, and texture for a particular use case, will it work as good on other platforms or not? With the new imagery and application requirements, we would require new features and then new methods. We are trying here by the proposed solutions to find a way to teach the network to learn the sensor specific details, and we move the boundary detection into something that can be learned in a supervised way, where it will learn for that particular application without going through the manually specifying the spatial, radiometric, and spectral characteristics. And we didn't tackle in this proposal the smooth transition between regions, but we did something interesting for the classification later on. Maybe we'll share it maybe in another presentation. Convolution neural networks, one of the deep learning techniques that can be useful in many applications. One of them is the boundary detection, as we've seen in our presentation today. Selecting the parameters of the architecture of the convolution neural network is done through trial and error, and we would advise to start from something available in the literature and try to modify each parameter individually until you get a good performance. You could also do, I think Google did that, where they train a network to select the parameters of another network, which is something could be useful. The other thing also you could try is what they call it transfer learning, where you have already available network trained on, like for your particular example, and then you try to retrain it on your particular data set. So you get something like, for example, this one, you train it on, as I did, you have all the parameters of the network set by my training set, and then you move the same network and you try to teach it a new data set. It is better than just starting from a random location. They call it transfer learning. So the idea is that you can transfer what a network has learned to a new kind of problem. We propose convolutional neural networks. we start from the input image instead of taking the full image. Maybe in some of your problems you will face problem with the data set you have, so you could work on batches instead of the full image. This will reduce the complexity also of your convolution neural network. We separated into boundary and non-boundary, and we increased the we balanced the data, the training set, so we have almost equal number of boundary and non-boundary batches. Train the network, get the output. This is the confidence map we get from one convolution neural network. We have many. We combine them. In terms of number of CNNs, through trial and error, we found that 3 through our experiments. And for decision fusion, there are many options, mean, median, or majority voting. We found the median to be the best. And for the selection of output, or we take all, sometimes some of the networks will degrade your performance, so selection was a good option for us. You get a final confidence map. It's good that if you have such a problem of boundary detection or even classification, you could use the Bragg texture dataset. This will allow easy comparison to state-of-the-art methods. We've talked about the precision recall and the measure. And we showed some images and comparisons. Thank you very much for your attention. We have time for a few questions.